All right, you are now being recorded.
Well, thank you, Brian, for being here with us today. I'm going to give a real brief introduction, then I'll have the teacher, Mrs. Morgan Randall, give a little introduction of a little bit about the school and what the group has been doing. This group has collected a lot of soil data, soil characterization data, soil temperature data, surface temperature data, and of course, soil moisture data.
All right.
And I think soil pH as well. One group was working on soil pH. So they've also been in the middle of a unit on soil, and the school is located in Central City, Toledo. So they're have been doing a lot of work just in the local community, looking at. Well, I'll let the teacher tell you a little bit more about what some of the things that she's been working on and partnerships with some other, maybe the zoo and the imagination station.
Oh yeah,
and so forth. So take it away.
yeah. So these guys, what we did instead of doing the whole unit on scientific method and lab tools and measurement and stuff like that, I kept that for the end of the school year. That way we can do all of this globe program and just kind of incorporate it into that curriculum. So basically, they've done all of these measurements, analyzed it, they have presented on it, so they understand it very well. And we've also watched some of your videos on there. So they've got good background knowledge on it, but they're really excited to meet with you. And recently what we've been doing is creating our own experiments. They're designing, based on their knowledge of soil and growth and pH and the types of soils, they're designing their own experiment top to bottom, and they're going to perform them those experiments in their groups soon. So we're collecting all of the.
And how about a little bit about the School for the Arts?
Okay, and Toledo School for the Arts, we are an art-based school, so we do a lot of art integrations. We did when we did our pollinator garden outside. These guys will get outside and paint the murals and fun stuff like that. So we're constantly integrating the arts into our academics. But they've also got classes like what do you guys take?
Dance,
orchestra, acting, theater. What else do you know? Art. All right. So they've got those electives incorporated into their school day as well.
Cool.
Yeah, it's really cool. So from the beginning, they're just very naturally creative people, and so that helps in science as well.
All right.
Yep.
All right, so let me go ahead and get started. So I'm going to talk to you a little bit today about the SMAP mission, Soil Moisture Active Passive, and it's a huge NASA satellite mission right now, giving us amazing amounts of data, literally terabytes of data a day of soil moisture. So I'm going to pop in here and share my screen. So, right. All right, can you see that?
Yes.
Yeah.
All right, so this is an image of our satellite, the SMAP satellite, Soil Moisture Active Passive. It was launched January 31st of 2015, and it originally started off with two instruments on board, an active radiometer, an active radar and a passive radiometer, and one of them stopped working a couple months after the satellite launched, but we're still getting amazingly accurate data for soil moisture using the radiometer. The radar stopped working, the radiometer is still working, but that's why we need your soil moisture data. Basically, we need soil moisture data from around the world to help validate the satellite data. So why SMAP? Why do we have a satellite mission called SMAP? And let me give you a quick little background is, in the science community, so scientists from around the world come together every 10 years and they try to figure out what is the most pressing and hot button topics that we need to focus on basically for understanding our planet's health and what really what scientists need to research as part of Earth to understand it better. And that's called the Decadal Survey. And in 2007, the Decadal Survey came out and soil moisture was in the top 3 things that scientists need to focus on. So NASA decided, well, we're going to launch a satellite to do this from space. Basically what happens is this satellite collects global soil moisture. It creates a global map of soil moisture every 3 days. What it also calculates if the soil is frozen or not based upon what's called the microwave signal that is being released by the soil up to the satellite. So it's really looking at the seasonality of how the soil is freezing and thawing throughout the year. So we're really looking in the area of the northern latitudes, what's called the Arctic boreal landscape, where it's an area where there's literally millions and millions of pine trees or coniferous trees that are going through a freeze-thaw state, and basically going through photosynthesis at a different rate at which they were in the past. And I'll get to that in a second. So why is soil moisture important? I mean, it's just simply, you know, we're taking measurements of how much water is in the ground. Who needs to know that? And there are lots of countries around the world that are really prone to landslides. Lots of deaths happen because of landslides every year. Areas where there's flood and droughts, areas where there's too much water, areas where there's not enough water. Agriculture is probably the biggest reason why we have this satellite in space, is that it really helps farmers understand when they can plant and harvest their crops. Through this thing we call climate change that NASA is really focusing all their earth science on, is we've seen a shift in when farmers can plant and harvest their crops. So farmers really need to know, and just understanding soil moisture can really help them out to really optimize the yield that they get for their crops. Also weather forecasting and long-term climate modeling and research. So what we're really looking for also in the SMAP data, the soil moisture data, is that we're looking for trends. We're looking for things that, we're looking for, you know, places where we see during particular global events like El Nino and La Nina, things like that. Are we seeing trends in where the soil moisture is greatest, where we're seeing it is the least? So we're really looking for trends across the planet. And these trends can help us predict, based upon future events that are going to happen, you know, where the soil moisture will be and where it won't be. So I'm going to pop over and show you this video real fast. And this is going to talk to you a little bit about how NASA studies our planet usually using SMAP, and it's called a whiteboard video. I'm gonna grab this here. This is called NASA Dishing the Dirt, and we create these for many of our satellite missions. So I'm gonna start that now.
Did you know that soil under your feet contains some of the most important water on Earth? And keeping track of this soil moisture is an important mission for NASA. Think of soil as a sponge. It can absorb a lot of water, but will eventually become full, or it can dry out as the water evaporates. Knowing when the soil is getting too dry helps us plan for droughts, prepare for food shortages, and identify places where wildfires can spring up. Knowing when the soil is too wet and can't absorb more rain helps us better predict floods and landslides. The best way to monitor soil moisture is not from the ground, it's from space. So NASA does this with special instruments orbiting high above us. Tracking soil moisture from space helps us improve weather forecasts and climate models. And it helps farmers know when to plant, water, and harvest their crops. Everyone on Earth benefits from the study of soil moisture. It's one case where NASA Dishing the Dirt is good for all of us.
All right, let me stop that. So that really shows you, you know, just why it's important. So why do you think it's important to study it from space? And that's a question directly to you guys. Why do we have a satellite studying it? Why can't we just take measurements on the ground?
Anyone have an answer? Karen, what do you think?
Because it could take forever just to get one area done.
Yeah, that's exactly right. It'll take forever just to get one area done. It's virtually impossible. We don't have enough scientists or instruments around the world to actually do that. So basically, you know, it would take a lifetime to just map, you know, more than a lifetime to just map every part of the United States. But the satellite, we can map our entire planet every 3 days. So we get a global map of soil moisture every 3 days from the SMAP mission. So let me pop back into this here. So that's exactly where we are here, is that here's an example of the map of the United States. And these are the active soil moisture sensors, ones that are basically stuck in the ground all across the US. And you can see there's lots of open spaces here. And you can see through the Midwest, you know, there's a lot in Oklahoma and Kansas and areas like that. But if you really look at it, it's very sparsely populated with soil moisture sensors. For instance, here is an example of what the SMAP satellite, this is done actually before the satellite, but this is showing you what one swath, right? A swath is basically the area that the satellite covers in one overpass. So you can see in one pass that this satellite will cover this much information. All this soil moisture data is coming back to the satellite. That would be right in here, and you can see there's lots of open spaces. But this is what it would cover. And getting a little technical, what SMAP is SMAP is called a sun-synchronous satellite. So basically what it does is it's a near polar orbit, so it flies across the poles, so across the equator, from North Pole to South Pole and back again. And what it does is it follows a 6 a.m., 6 p.m. local time traverse of the equator. So it crosses the equator at 6 a.m. and 6 p.m. local time as the Earth rotates. You all may be familiar with the Coriolis effect. We've got the Earth rotating all the time. So anything flying around it is relative in perspective, but the satellites have to follow a certain path. There's geosynchronous, there's sun synchronous, but this one has to be sun synchronous. So it basically travels across the equator at 6 a.m. and 6 p.m. local time. So that's when the best time is to take measurements around 6 a.m., 6 p.m. in your local area. So the SMAP mission can cover a lot of information in a short amount of time. We use what's called the microwave part of the spectrum. I know you've all probably seen the electromagnetic spectrum that runs from radio waves all the way down through gamma rays. We're in the microwave section. So what happens with the satellite, and because I mentioned that we only have one sensor working, the active passive sensors, the active one is the radar, which isn't working, but when it was working, what it did was it sent a radar signal down to the planet, and the radar signal penetrated the Earth's surface into about the top 5 centimeters or 2 inches of the soil. It bounced around, and it sent an energy value back in the microwave sensing range. And those numbers, via algorithms created by some really smart scientists and engineers, is converted into soil moisture measurements. Unfortunately, you know, that gave us high resolution data, but we don't have that high resolution data anymore. What we still have, though, is the passive sensor, which is the radiometer. And what the radiometer does is it basically reads the microwave energy that radiates from all celestial bodies, including the Earth. So what happens here is that all the soil naturally emits microwave radiation. And the onboard radiometer collects all that energy, all that microwave energy that is being radiated from the Earth's surface. And those numbers are then converted via algorithm again. Algorithm is just a way to take the data, take the numbers that they get from the energy, and basically convert it into soil moisture numbers. So if there's a high energy readout from the soil, that means the soil is very dry. If it's a low energy readout, that means the soil is very wet. And then everything in between. So those numbers are then converted into basically percentages, you know, 0 to 100% soil moisture. So the satellite is now giving us very accurate data. It's just the resolution isn't as good as we like it. With the two combined, we had about a 9-kilometer resolution. So that means that the satellite could focus directly on a 9-kilometer resolution, but then you can also look at areas a little more specific, but you won't get as accurate resolution. We're hoping to, and we're working with the European Space Agency. The European Space Agency has a satellite called Sentinel, which actually flies directly behind the SMAP satellite. And it uses an active radar, just like we had on the SMAP satellite system. And we're hoping to grab that signal to use it for what we need to get as far as getting our high resolution data back. I mentioned earlier that the SMAP mission is also measuring surface freeze thaw. And that's important because it helps us understand our carbon budget. We have areas in the Arctic boreal landscape, as I mentioned earlier, that have millions and millions of these pine trees or coniferous trees. And what is a process that trees go through and plants go through all the time in order to survive? What's the process called?
Photosynthesis.
Right, photosynthesis. So it's basically the intake of carbon dioxide and converting that to oxygen. What we've seen over the past is that when these trees they live in two states. One is called an active state, where they're basically alive and going through photosynthesis at a normal and even accelerated rate. But then there are also periods when it's dormant, where basically the trees are asleep and they're not going through photosynthesis as quickly as normal. So what happens here is that when the trees are basically alive during an area when the soil is thawed or not frozen, and then they go into a dormant state when the soil freezes. So what happens here is we've seen that there's a change in the time that the soil is actually frozen. It's shorter. So that means the trees are alive for a lot longer, going through the photosynthesis at a normal or accelerated rate, thus pulling what out of the atmosphere? What are the trees pulling out of the atmosphere?
Carbon dioxide.
Carbon dioxide. So it's pulling, we have a lot of excess carbon dioxide that contributes to the whole global warming, climate change thing. So this is actually a benefit that, we're seeing the soil is frozen for a shorter period of time. So therefore, we can then see that we're getting actually more carbon dioxide pulled out of the atmosphere by these trees. And that all depends upon how the soil is frozen or if it's thawed, and the satellite can determine that. So in order to get really amazing data in a short amount of time, we put together a video called Technical Origami that explains why the satellite can do this, why the satellite can take measurements over a large area. It has what's called a 1,000-kilometer swath or a path on the ground. So it's collecting data from 1,000 kilometers at any given time. So think of it as a big circle on the Earth, where the whole diameter of that circle is 1,000 kilometers. So that's a pretty large area. So that's when it's collecting data all the time as it's flying across the Earth. But in order to do that, we had to go through some awesome technology. So this video will show you just how much the engineers designing this antenna have gone through in order to make sure that it works. And one thing you'll hear in the video is that they had to figure out on Earth how to get this antenna working and rotating in a zero gravity area. And they can't just test it anywhere for zero gravity. So you'll see they have to test individual parts of it. So I'm going to pop out of the presentation again and go to this technical origami video.
Deploying large structures in space is one of the most difficult things NASA does.
The antenna, the computer, the thrusters, all of those things have been used before. But when you put them together in this system with this large rotating antenna, what you get is a pattern that covers the entire planet. And with that comes some engineering challenges.
What we need to do is develop an antenna that's very small before we launch it, and then it blooms out to a much larger antenna on orbit. That's one of the big challenges for SMAP.
There's a 20-foot antenna at the top of the spacecraft. When you look at how that system works, this large umbrella-like looking thing collapses down just like an umbrella would, folds at the elbow, and then folds again back along the side of the spacecraft. Packaging that bit of technical origami is a real trick.
We need to test the antenna on the ground like it will be deployed in space. But the antenna was designed to operate in zero gravity, which makes testing on the ground quite challenging. We can't just simply deploy it on the ground and then spin it up. So what we have to do is test the whole system in pieces.
First, we look at what it takes to sort of balance the spacecraft. Then we look at how that whole system behaves together when you spin it.
We test the reflector extensively by itself. We test the boom that deploys it by itself. We also have a very challenging thermal environment on orbit. It can see 100 to 200 degrees variation in temperature.
We take the data that comes from each one of those little tests and we put it into the model to describe the end-to-end behavior of the system.
Testing and testing and testing. And we test a little more until we're convinced that we've tested all the different environments and met all the requirements of the system.
We considered every scenario from science and engineering, physics that we could imagine. It's human nature that you always would like to do more, to be more convinced. But there's a fine line between testing too much and breaking something, and testing enough and convincing yourself it's good.
We've gone through at least 10 to 12 deployments just while it's been here, and most of them have been successful. A few of them we had problems with, and we worked with the team to figure out what the problem is and resolve it. And then we've had 3 successful deployments right before we shipped it, and they were all picture perfect.
This is probably one of the greatest accomplishments of any of our lives. It's not often you get to be part of a mission that has a global impact. You know, as children, we all imagine someday being able to do something that'll change the world, or somehow being heroic, and being able to contribute to the strength, to the health of the planet, and to the human race is incredibly powerful.
All right, so that the large dish antenna that you saw is made of actually this material I have here. I don't know if you can see this, but it's actually, it kind of looks like pantyhose, but it's not. What it is it's actually a metal. If you ever see on the periodic table called molybdenum, have you ever seen that? Yeah, look down there. Can anybody find out what number it is on the periodic table? I see your periodic table there. It's like starting in the middle and the bottom, somewhere in there.
What up above
I
the
think it's MB.
MB. NB or MB?
M, molybdenum.
Oh.
101.
Oh my gosh.
Anybody find it?
Can you say it, Haley?
So while you're looking for that, what this is this is a gold-coated molybdenum. So it's a very strong metal, but it's a very malleable metal that can be made into these really thin wires. And basically, we coat it with gold. We coat it with gold because that's a great reflector. Gold is an amazing reflector of sunlight, but also that because the antenna is made of the molybdenum and the gold coating, it can actually grab those microwave energies from the soil. So it's very strong. If I were to pull this as hard as I can't break it. It's just amazingly strong. Anybody find it yet?
I think it's 101.
101? I don't know. I haven't even looked it up on a chart yet, so I guess it's 101. Yeah. So basically, it's one of those elements that are way up in the periodic table. But I asked some of the engineers, why did you design it with molybdenum? And they said because it's very strong, but it can be converted into a very fine wire to make this mesh. And remember, there's a video they showed you that antenna has a 20-foot diameter. So it's really big. And as it rotates, as it's traveling around the Earth, it allows you to have that 1,000-kilometer path in which it's collecting the data. I'm going to pop back into here again, and then we'll talk a little bit about why it's so important, to take the measurements. Why it's important to take the measurements. So we have what's called, as you know, the GLOBE program. And we have running right now is the SMAP soil moisture measurement field campaign. And this is basically collecting data via the SMAP block pattern soil moisture protocol. And what's very cool about this satellite mission is that you can actually take the data and get the same data that the satellite is taking. So it's very important for many reasons. One, that you can understand how the soil moisture is affected in your local area, in your local environment. You can also compare it to other schools across the world on any given day through the GLOBE program. But also we have lots of SMAP scientists on board, from our team that are really looking at the data directly. They're looking at how the student GLOBE collected SMAP block pattern soil moisture data compares to the satellite data. So we actually have countries, we have 8 countries participating right now, and you'll see Croatia, the US, including Puerto Rico, Trinidad and Tobago, Italy, Israel, Oman, Egypt, and Thailand. So we have a good representative all across the world. It actually looks here that we have some in China, but those are just test sites. They were just testing latitude and longitude, so those aren't actually real sites, they're just virtual sites. Also the one out here that's in the middle of the ocean, so that doesn't work. Can't collect soil moisture in the middle of the ocean. So, but we have over 2,000 soil moisture measurements taken, and this is really important to help validate the SMAP satellite data. So what we have here, we have these grid spaces as part of the protocol, which are 3 meter by 3 meter grid spaces where the samples of soil are collected, and then basically, you know, you take the you take the wet mass, which is you collect the soil and weigh that mass, and then you dry it via a soil drying oven or a heat lamp, and then you take the dry mass, and then you can calculate basically the volumetric soil moisture because you have a can or a bag which has a given volume. So one way that we can look at the SMAP data is what's called in worldview. Worldview allows you to grab the data and look at where, you know, by day, look at what the SMAP mission covered, what the satellite covered. And this type of map is also available on the globe visualization map. And the scale that goes along with it will allow you to look in your area and zoom down and basically figure out if the numbers that you collected of the soil moisture data match up to the satellite data. But this you can check it with any day. So what we're looking for, as I mentioned earlier, we're looking for the trends in data. You'll see out here, there wasn't much of a trend. This is a comparison between globe data from the Varison school in Croatia, comparing it to the SMAP data, which is the red line and dots. So we focused in the middle of April, we got started. But what we have here is we chalked this up, that it doesn't match up to each other. The soil in Croatia was just starting to thaw. So they were just finishing winter in the mid-April in that latitude. And we saw there was a lot of freezing, so there was some user error in that. But once the soil thawed out, we just started seeing these, even though the numbers don't match up completely, what we look at here are trends. And we really see a trend in this data. So we can say that the data that the students collected in Croatia matches up with the satellite data. The numbers aren't specifically the same, like this is 0.05, and this is 1.15. They're not exactly the same. What we're really looking for are the trends, because there will always be some type of user error when you're doing it, just collecting the soil from the ground. There'll always be a little error. But that's why it's so important to collect this data, because one, you're helping out, you know, understanding your own environment, but you're also helping NASA understand the global picture of soil moisture and how it affects the planet. Because as I showed earlier, that there's so many things that just understanding soil moisture can really be applied to.
Brian, we got about 5 more minutes.
All right, perfect. So we have what's going on right now is called the Globe El Nino campaign. And as you may know, we're right in the middle of an El Nino phenomenon. I should say we're at the tail end of an El Nino phenomenon. It's kind of winding down. But it's a climatic phenomenon that can have impacts globally, causing flooding and droughts, as well as causing changes in seasonal weather across the planet. So one thing we do notice is we've actually had some countries like Peru where it's been unseasonably hot, and there have been some deaths related to El Nino and heat stroke. So areas like that are a little cooler this time of year have just gotten really, really, you know, extreme heats and for long periods of time. And this is all due to El Nino. But in order to understand how El Nino is affecting a local environment, we can take measurements via some of the globe protocols. And we have teachers and students taking measurements in these protocols: precipitation, air temp, surface temperature, soil temperature, SMAP, and biometry, canopy, and ground cover. And I know you guys, as I heard earlier from your teacher, you guys are taking a bunch of these measurements now. So by doing that, you're actually participating in the Globe El Nino campaign, because we require the students to collect data from at least 2 of these protocols. And we do that because, you know, in order to really see how the El Nino is affecting the globe, it's good to compare at least 2 protocols. We can see how precipitation is being affected by, you know, say air temperature. We can see how soil moisture is being affected by precipitation. We can see how canopy and ground cover is being affected by soil temperature. So they all have ways to compare with others, with other protocols. So I will leave it here and I will pop back in. This is some resources that your teacher can share with you, but it's ways to really show you all about the SMAP mission, how you get involved with Globe. And also we have some NASA Know Your Earth quizzes, and all the way down to areas where you can look at really cool NASA videos. So I'm going to escape from this and then come back out of this.
Some of the students have some questions, Brian, if you're...
Yeah, for sure.
Hey, ladies and gentlemen, we only have a few minutes, so if you could look at your questions, both the ones you wrote up and the other classes, and if he's already answered those, let's not ask those questions, okay? Who would like to go first?
How can you track the soil moisture during an earthquake?
How can you track the soil moisture during an earthquake?
Yes.
Oh, that's a very unusual question. I've never had that one before. That's pretty cool. But yeah, it would just be tracked like the same way. You might get a little little shimmy in the data, but it would just be because the satellite's flying above the Earth. It doesn't really have any. The earthquake doesn't have any effect, on the soil moisture data that's being collected. I had to repeat that. I couldn't hear that.
Speak up.
How many miles is the spacecraft from Earth? How long does it take to get up?
How many miles is it from Earth, and how long did it take to get there?
So it's approximately about 400 kilometers above the Earth's surface, and that it varies. Its altitude increases and decreases based upon its flight path. But it took, and actually I don't know, I had a video, but it actually, to get out of orbit, it only took a little under 2 minutes to get out of the Earth's gravitational pull, where we could separate the satellite. And then once the satellite got into space, it had to go through a series of maneuvers. The first thing it had to do is it had to orientate itself so it could open up its solar panels, because we know the solar panels, we always want to be facing the sun so we can grab as much energy as we can to keep the satellite working. And then it took, several more weeks for the actual antenna to slowly open up and expand out and then start rotating. So every little piece that gets, every little piece that's part of the satellite takes a while, at least several days to get working, because we have to make sure everything works properly. And when we launched it, everything worked perfectly up until a couple of months after the one instrument stopped working.
So for everybody, that's like from here to Columbus. That 400 kilometers, and that'd be about right, I think. I did some quick math in my head. That's how far away the satellite is, except instead of south, straight above our heads, right? So,
What gave you the idea to create SMAP?
Is it what was the idea how we created SMAP?
Yeah.
Yeah. So as I mentioned earlier, that the scientists got together and they decided, soil moisture really needed to be one of those things that NASA scientists and scientists around the world studied. So NASA said, hey, we have the opportunity, we have the resources to build this satellite. Let's build it and let's have it study soil moisture.
last question, Karen.
How long did it take to build SMAP?
How long did it take to build SMAP? Is that what it was?
Yep.
Okay, so that's a great question. So we started with SMAP. We started building SMAP in about 2009, and it took basically what happened. The radiometer was built at one NASA center. It was built at the Goddard Space Flight Center in Maryland, and then that was shipped out to the NASA Jet Propulsion Laboratory in Pasadena, California, and then they built the radar and then built the antenna and then the rest of the satellite. So that entire process of starting it for the first thing that was starting to be built until it was launched, or I should say finished building, ended up being about 5 years.
All right, it's lunchtime, Brian. Thank you.
All right.
Brian.